In a powerful stride toward unlocking the full potential of quantum computing and communication, researchers at Rijken and the University of Amsterdam have solved a foundational puzzle that has lingered in the quantum community for over 2 decades. Their breakthrough, an exact mathematical expression for a key part of entanglement distillation, represents a vital turning point in the quest to produce pure, robust quantum states. While the full realization of this work in practice may still be years away, the implications are immediate and profound, injecting a sense of renewed optimism into a field that's often slowed by its own complexity. Quantum entanglement remains one of the most mysterious yet fundamental features of quantum mechanics. In this deeply non-classical phenomenon, particles become inextricably linked so that the state of one instantly influences the state of another, regardless of the distance between them. It is this phenomenon that underpins much of the promise surrounding quantum technologies, from ultra-secure communication to quantum-enhanced computing power. But in practice, entanglement is difficult to achieve and even harder to maintain. Real-world quantum systems are riddled with noise, interference, decoherence, and other distortions that muddy the purity of entangled states and compromise their usefulness. This is where entanglement distillation comes in. Much like refining raw materials to extract a usable product, this process takes numerous noisy entangled pairs and filters them down to a smaller number of high-quality, purer ones. The difficulty lies not in the idea itself, but in its execution. For years, scientists have struggled to calculate the precise rate at which entanglement can be distilled from impure sources, especially under general or realistic conditions. This lack of clarity has been a major theoretical bottleneck, one that affects everything from quantum cryptography to scalable quantum networks. The recent work by Dr. Bartosz Regula of the Rijken Center for Quantum Computing, in collaboration with Dr. Ludovico Lamy, represents a genuine breakthrough. Not only does it fill a critical gap left by earlier, flawed attempts to link entanglement distillation to relative entropy, a central concept in information theory, but it also redefines what's possible at the intersection of quantum theory and mathematical precision. This is only the second time an exact expression for the distillation rate has been successfully derived, and it does so under a broader set of assumptions than ever before, greatly expanding its potential relevance. The importance of this development cannot be overstated. It equips scientists with a more accurate and generalizable framework for understanding how to convert noisy entanglement into a usable form. The implications for quantum computing are particularly exciting. Quantum computers, especially those built on entanglement-based architectures, rely heavily on the availability of clean, reliable quantum correlations. Better understanding and optimizing entanglement distillation could mean more robust qubits, more reliable computation, and faster progress toward truly practical quantum devices. It also has strong implications for quantum communication. Technologies like quantum key distribution, which promises unbreakable encryption, are critically dependent on entangled photon pairs. These communication protocols are currently hampered by losses and noise, especially over long distances or in real-world environments. This new mathematical clarity could inspire fresh engineering approaches to manage these challenges more efficiently, increasing the reliability and reach of quantum-secure networks. Of course, there remains a gap between theory and laboratory application. As Regula notes, the new expression is based on approximations involving large ensembles of quantum states, much larger than current experimental setups can handle. Today's experimental quantum systems can manipulate tens or maybe hundreds of qubits. To fully test the theory, researchers would need to control and measure quantum states in the thousands or beyond. But history has repeatedly shown that theory often outpaces technology, only to be vindicated years later. This latest breakthrough pushes the theoretical frontier forward, setting a new target for experimentalists to pursue. Beyond the direct applications, the result also reaffirms the power and importance of pure theoretical work in quantum science. In a field often driven by engineering challenges and material limitations, it's easy to lose sight of the elegant mathematics underpinning it all. This discovery is a vivid reminder that conceptual rigor and mathematical precision still play an essential role in charting the course of technological progress. In the end, this is more than a victory for two researchers or a single institution. It's a hopeful signpost for the entire quantum research community. It proves that long-standing problems are not insurmountable, that errors in the past can be corrected with care and creativity, and that the pursuit of pure knowledge, patient, precise, and persistent, continues to yield treasures. With this puzzle now solved, the map to a purer, more powerful quantum future becomes clearer than ever.